As Yan Van introduced, I'm Andy Campbell. I'm the director of SEAS, Synchrotron Earth and Environmental Science. I was asked to say some words here this morning because we're co-sponsoring, this workshop. And SEAS is an organization that manages, NSF support for synchrotron facilities around the country. And, we help make possible a variety of experiments in earth and environmental science, not just rock deformation. I'll try to actually emphasize all the other things that SEAS makes possible, because I know you're going to hear a number of talks today about rock deformation. But synchrotron facilities supported by SEAS, you provide a wide range of X-ray based applications for earth and environmental science applications, X-ray diffraction and related scattering methods, X-ray microprobe techniques, including fluorescence and absorption spectroscopy, tomography applications like those that you would use in rock deformation, we showed in the previous talk, tachography and other coherent scattering methods. Nuclear resonance scattering is done at Sector 3 here, and we have one beamline that's not for X-ray purposes, but infrared, synchrotron infrared spectroscopy at NSLS2 at Brookhaven National Lab. Now, as I said, I'm not going to focus so much on rock deformation methods because I want you to be aware of all the other techniques that SEAS provides the earth and environmental science community. Over my career, I've used most of these applications here. You're at the beginning of your career and you're focused on rock deformation right now, but you might, as an experimentalist, it's helpful to just always be aware of all the other applications people are using, in adjacent fields. You never knew when that might be useful or when it might, take you off in a new research direction, maybe using some of these other methods for characterization of your recovered sample products or characterization of your starting materials or just some, related cool applications. So I hope you'll appreciate the variety of things we do. And these methods are applicable not just in rock mechanics, which is the focus of this workshop, but a wide range of other earth and environmental science applications. Basically anything where you've got materials that you want to, characterize, things that you want to measure, either natural samples or experimental run products or in situ experiments, anything that's about materials characterization, especially if, in general, probably has some sort of synchrotron-based application. I'll show examples today, depending on how well I manage time, whatever, paleontology, low temperature geochemistry, basically most of these. So as I mentioned earlier, SEAS operates at 4 synchrotron facilities. We are here at the Advanced Photon Source, where there's maybe half a dozen experimental stations that are supported by SEAS to varying degrees. We've also got a handful of experimental stations at the Advanced Light Source supported by SEAS. There's a person at SSRL at Stanford who supports X-ray microprobe applications around the ring. And we've got activity at least 3 experimental stations at NSLS2, the National Synchrotron Light Source at Brookhaven. The purpose of SEAS, so SEAS formed 2.5 years ago. It was a merger of pre-existing organizations that were managing synchrotron facilities for earth science applications, but not just a merger. We also expanded in a couple of targeted directions, and rock deformation is one of those areas that we specifically invested in, and that's part of why this workshop has happened. But we've got 4 main goals, I think, right? Developing and operating these beam lines and making them available for the earth science community. We improve on the technology, taking advantage of new instrumentation or new development of the beam lines themselves. For example, the UPS has just undergone an upgrade over the last couple of years and has got enhanced capabilities relative to what it had prior to the shutdown. The Advanced Light Source is planning one of those in the next couple of years. NSLS2 is planning one much more longer range. We interact with the earth science community quite a lot, sometimes through activities like this, but mostly really through the interaction with the beamline scientists at the beamlines. So we sort of gauge the pulse of the community to identify what are new opportunities and new experimental techniques that maybe we should be supporting. and of course, outreach and education programs to develop the next generation of scientists. As I said, we started in 2023. We're on a 5-year cooperative agreement, meaning we would hopefully be renewed in some form 2.5 years from now. When I made this slide, at that time, we were supporting to varying degrees 36 people, mostly at 100%, but not all of them. And many of these are beamline scientists, but there are others as well. SEAS is hosted organizationally at the University of Chicago, where I am, and where Emily is. But the GSE CARS staff are also U Chicago employees, including our Chief Technology Officer, Mark Rivers. And to help manage the beamlines around the country, we also engage with subaward subcontracts to other universities, Santa Cruz, Minnesota, Illinois, UIC, University of Illinois, Chicago, and Stony Brook and Stanford. And each of these, in turn, manages beamline stations at, with different applications, at different synchrotrons indicated here. The way we work is SEAS funnels NSF support to support beamline scientists and experimental equipment, and we negotiate with the synchrotron facilities, which are operated by the Department of Energy, and we say, well, we're going to invest in this beamline, and in exchange, we would like some sort of preferred access, and the deals vary from place to place. Here at GSE CARS, basically 100%. It's largely managed, but at the other stations, it's not always 100%. We negotiate for a certain amount of time that has been sort of a preferential time for Earth and environmental science users. So we leverage our investment in the beamlines to make it more available to the Earth and environmental science community. And these are called approved programs, partner user agreements, and biovirtual. Now, the SEAS team, unlike other partner user agreements and other approved programs at DOE facilities, we don't keep all this research time ourselves. Instead, we make it available to you guys. And the beam time is mostly allocated on a proposal basis. You would submit proposals. In fact, there's a deadline coming up this week. Is it Wednesday? So I hope it's a productive workshop. We can or next time's fine. We're operating this workshop and operating these beamlines because we want you and the rest of the community to submit proposals and use the facilities that we're investing in, right? We're doing this for the user community. And as I say here, the general user system is the basis for most of our beamline assignment, even time assignment. We've got a variety of outreach and education activities. This workshop is an example of that. The beamline scientists at all our facilities are forever collaborating with other, user-initiated or facility-run programs. We've got a website that's, like all websites, under the process of, we hope, continuous improvement. It's continuous. I hope it's improvement to make, information available to the user community to better identify what, SEAS facilities can do for you and which is the right beamline. We've got a variety of other, outreach activities, including our annual user meeting, which when Lou flashed up in the previous talk, this year's annual user meeting will be held here in Chicago, August 8 to 10?
10 to 12.
10 to 12. 10 to 12, yes. So hope to see you there. As I promised, I wasn't going to say very much about in situ rock deformation studies, and that's true. But as you saw in the previous talk, it's as I said earlier, we have focused specifically in investing in situ rock deformation applications at a variety of beamlines because when SEAS was coming together and we were developing the proposal to create SEAS, one of the sort of sub-communities that had been identified as probably underserved or anyway underutilizing the capabilities of synchrotrons was the rock deformation community. So in situ rock deformation using X-ray sources is certainly a focus that we've had. And as part of that, we have made we've not only continued to support the existing beamlines, but we've made new investments at a variety of beam lines across seas, specifically to support in situ rock deformation and particularly, I guess, sort of upper crustal conditions that Wen was focusing on. We've, in addition to continuing the rock deformation studies at sectors 6 and 13, we've made new investment at sector 6 with new stages for tomographic applications. We've invested recently in a staff person at ALS Beamline 832. And I don't think Wenlu mentioned, but we've also provided support for general user experiments at this powerful hex beamline at NSLS2, as well as investing in workshops to support the hopefully growing in the rock deformation community. So we're doing this because, as I said, we hope that you will apply for beam time, right? You're here to not only, learn about the techniques, but also to become, activated as users. Yes. Back to that later. Okay, having said that, I really want to focus on all the other applications because this is the one chance you have, I guess, to hear about all the things that SEAS does that isn't rock mechanics. So I'm kind of going to go through and give you some what I consider scientific highlights of the last couple of years using many of the techniques that were discussed in the early slides. And if you want to get me on track anytime or if you're running over time, just shout out. I don't remember when I started.
It's fine.
When did I start? Was it 9:30?
You're about 10 minutes late. So
okay, I'm good.
No worries.
Okay. So tomographic applications are something that you're going to be seeing a lot of that you already saw in Wenlu's talk, but there's a lot you can do with tomography and earth and environmental sciences besides rock mechanics. Here's an example of, let's see, when was this published? Last year. This was a Nature paper in 2025. This is a paleontology example where this postdoc, Yara Hariri, was investigating, trying to date sort of the earliest stages of vertebrate evolution. I guess there had been postulated fossils from the Cambrian period where they said these are the teeth of vertebrate animals. And she did this X-ray tomographic study sort of comparing those fossils to a variety of other fossils, including some modern arthropods, and demonstrated with detailed, analysis of the internal structure of these fossils that those things that were being called teeth or early teeth-like features, they weren't teeth at all. They were just some sort of other sensory organs that are more like what you see on crabs and other arthropods. So through this study, she kind of pushed that forward so that the development of teeth and vertebrates, the earliest evidence for that is not the Cambrian, but in the Middle Ordovician now. Oh yeah, and then another, I guess these are great images that I just wanted to share showing sort of details of the sensory organ structure that they're able to get here. And this work was done here at 13 BMD. Let's see, I guess still on the theme of tomography, but this is a study that combines X-ray tomography with X-ray diffraction. This is somewhat older, but this kind of work continues. This has become sort of a sub-area of study, I guess, of investigating the inclusions within diamonds. Diamonds travel from significant depth in the earth. Some are thought to come from the lower mantle, and those are the ones, that they were targeting here. It's tricky to analyze these inclusions, these minerals that are formed inside, captured inside the growth of diamond. But when they are identified as being the type of mineral that only exists in the transition zone or lower mantle, then that's exciting for those who are trying to, seek direct samples from those great depths, which otherwise, we only access by experiment. But getting information on those is tricky. What this group did, which also I think was at 13 BMD, so that's right here actually, is they found these diamonds that were, putative deep-seated deep origin diamonds, and then scanned them with tomography to find the mineral inclusions, which otherwise are really difficult because diamonds got very high index of refraction and they're irregular and difficult to polish into easy shapes. So, how do you get good optical access? It just doesn't really do it. So they use tomographic imaging of the diamond grains, and that helps locate where the inclusions are, and then go in with the X-ray beam to get X-ray diffraction on the grains to identify what are the minerals there. And this is a way of identifying, these diamonds came from I don't remember this particular one, but anyway, great depth. Transition zones. Some are thought to have origins even at the upper part of the lower band. Okay, and then that sort of leads me into just mineral physics in general, which, the mineral physics community, especially, well, both the large volume press and the diamond animal cell community, studying deep earth applications. We've been using X-ray synchrotron applications for decades, and which is not to say that other earth and environmental science fields haven't, they have, but the ability to peer inside the experimental apparatus was early on recognized as so important for the high pressure mineral physics community that it has taken up a sort of disproportionate, a large fraction of the synchrotron using geoscience community. Using X-ray techniques, mineral physicists study phase equilibrium equations of state, vibrational spectroscopy, in situ rheology, rock mechanics properties, acoustic properties, and transport properties. C supports mineral physics applications at quite a variety of diamond animal cell beamlines, DAC, that's diamond animal cell beamlines, at APS, NSLS2, and the advanced light source. All these beamline scientists are diamond cell oriented. We've also got, I hope I've got everybody here. A handful of large volume press beamlines, and some of those large volume press scientists are here in the room for rock deformation applications. The techniques we use are similarly, broad. I think because I know that we're trying to catch up on time, I'll try to go very quickly through this, but you can see with both diamond animal cell and large volume press experiments, there's a broad range of X-ray and infrared scattering techniques that we use, sort of mapping on to what I said early on in the talk. You're going to be seeing large volume presses this afternoon, I guess. Here's one at IDD with a couple different tooling sets. One's hidden behind my blue there, and but there are similar large volume presses at a variety of other beamlines, including the Max PD program. Matt, are you presenting this week? Maybe you'll show some pictures like this.
Will not, but yes.
Okay. I'm glad I showed this. So that's the one at NSLS2. Again, I'm not going to spend too much time on rock deformation applications, but you can see there's quite a variety, and I imagine you'll be hearing again, Ben, this is your slide. Thank you. But there's quite a variety of tooling that goes in those large presses, some of which are for deformation applications, but others are for tomographic applications or structure of liquids. The carbide tooling that goes into the large presses is very versatile and provides a lot of different types of investigation of material properties at mantle conditions. I have a couple of highlights that aren't rock mechanics. Here's sort of bread and butter mineral physics. That is, what is the density of something as it changes under pressure and temperature? Or what are this one is acoustic wave velocity. So these are sound velocities and sound velocities and density. So, elastic properties. This one is an iron nickel alloy, a couple different compositions with applications to various planetary bodies, Mars, Mercury, and the Moon. We don't have seismological data on Mercury to compare this to, but we do have geophysical data. And there's actually, a growing understanding of the seismological properties of Mars and the Moon now. So let's see, I think this also, again, did I also get this one from you? Yeah. Okay. Yeah. Right. So, and my video is working. You can see these are falling spear experiments, where this is a molten albite, and I wonder if I can do that again. There we go. And when you raise the temperature and melt the albite, then you can see the tungsten bead and then the radium bead descend. And by knowing the density and the size of the bead and its velocity, one can infer the viscosity. And in this study, they showed that the viscosity goes through, it initially decreases, but then increases with depth, and it makes them inferences about the geophysical consequences of this changing viscosity depth. Okay. Most of the rock deformation studies are done in large volume presses or in low pressure apparatus that still have samples of pretty significant volume. When you get into higher depths, greater depths in the earth, then the techniques require sort of miniaturization and you get into the diamond anvil cell. There aren't the same well-developed applications for rock deformation in the diamond anvil cell, but there's sort of the beginning of it in the form of yield strength studies. So these are radial diffraction studies in a diamond anvil cell. This one goes up to, I think that says almost 60 GPa, where they're using a diamond anvil cell. And instead of having the X-ray diffraction go through the diamonds, axially, they go through the side, and that sort of that probes a variety of deformed states of the minerals. So you can sort of see from the diffraction rates here, you can infer the yield strength of the material. And then what they've done in this study, okay, weirdly, temperature increases over here, but it also increases going up over there. But anyway, as the temperature increases, then you can see the material becomes less deformed. It relaxes, and the stresses become, more homogeneous. So that's the radial diffraction study, and this is a relatively new technical application that was just published last month. Diamond anvil cell programs are a really big part of what happens at Sector 13 here at the Advanced Photon Source. There's a couple of beam lines, three, right? IVD, BMC, and BMD all have diamond anvil cell components to the activities there. For those who haven't experienced it, this is a diamond anvil cell. It's nearly 2 inches in diameter. And just by turning the screws, they achieve really high pressures. And then there are lasers. I think I've got, by focusing laser beams through these microscopes and into the diamond anvil cell, which is held here, they achieve temperatures of thousands of degrees Kelvin. And while the sample is under those conditions, the X-ray comes from the right, scatters off the sample in the diamond anvil cell, and is recorded on the detector over here to the left. And I'll try to go quickly through some applications here. This one is a recent last year study in Nature Communications focused on the specifics of the phase diagram in the Mg2SiO4 system. These transformations at 23-ish GPa that characterize the change from the Earth's transition zone to the lower mantle. I mean, these phase transitions were known in the 1970s. And here we are in 2025, still getting Nature Communications papers, out of that very same transition. So, to me, it's remarkable that we're still getting really, increasing detail about something as fundamental as the spinel to perovskite transition in Mg2SiO4. So it's either a testament to our field or a condemnation. I'm not really sure. I'll be the judge. Something I'm excited about in terms of diamond anvil cell X-ray diffraction applications is the growing technique of single crystal X-ray diffraction on multi-grain samples. If you know anything about X-ray diffraction, you were probably taught about X-ray powder diffraction, where you've got thousands of grains and you're probing them all in random orientations and you get a powder pattern. Or you were taught about single crystal X-ray diffraction, which is less convenient but more powerful. It gives you the sort of more detailed atomic structure, the crystal structure of the mineral. In really extreme conditions of pressure and temperature, you don't get to choose whether you've got a single crystal or not. You just make the sample, and it's either powder or it's a hardly ever single crystal. And most commonly, when it's really a small sample and it's been heated to thousands of degrees, most commonly it's somewhere in between. It's like dozens of grains or hundreds of grains, not thousands. So it doesn't really make a good powder pattern, and it doesn't really make a good single crystal pattern. But there are these relatively new, a decade or so, but it's increasingly popular methods that involve basically sort of doing single crystal diffraction, collecting the data over whatever is the available range of rotation, and then trying to figure out all the single crystal data simultaneously, or at least grain by grain. So I pulled out some slides about the technique for efficiency here, but basically from a series of powder patterns, core crystal or core powder patterns that looks like this, right? You extract in the reciprocal space, a set of grains that make sense in relation to one another and appear to be a single crystal, and then do structural refinement of only those diffraction pieces. And here's an example that was done. This one's Zurkowski et al. That's my group in 2022. This was at 193 GPa and 3000 Kelvin. The sample was synthesized under those conditions, quenched at room temperature, and then the data were collected to figure out what we got. And what she found was, a new phase, a new iron sulfide phase that only exists at the pressures and temperatures of Earth's core. This is the structural refinement. You can see it's very complicated. We never would have got this kind of information from powder X-ray diffraction. It really requires a single crystal method. But also, if you really want to understand what are the mineral phases, deep in the Earth, you need to do the single crystal diffraction. So there's a lot of, it looks funny here because there's a lot of positional disorder in the structure. It's a really messy structure, but I'm proud to say that we figured it out. And it turns out it's pretty important in an iron sulfide system. Coexisting with HCP iron, this phase Fe5S2 exists along the liquidus, meaning that as a metallic core cools at really high pressures, this phase will form. It may exist in Earth's inner core now, but if it doesn't, it will. But it's the sulfide phase of the saturated iron. Okay, how am I doing on time? Pretty much out. 2 minutes. 2 minutes. All right. Infrared spectroscopy is this is a unique beamline at the FIS program at NSLS2. Infrared spectroscopy is a terrific complement to X-ray diffraction or X-ray studies in many applications because it gives information, vibrational information, and it's really commonly used to understand hydrous phases. Here's an example. This is the phase H type material. It's a complicated solid solution that's thought to be probably the most abundant hydrous phase in the lower mantle. It's thought to be the bearer of hydrogen in lower mantle compositions. And this group earlier this year published this paper showing the symmetrization of hydrogen bonds as you go to increasing pressure in this material. The symmetrization of the hydrogen bonds is important because once the bonds are symmetrized, I guess, they become stiffer, right? So it changes the compressional sort of options of the crystal as you continue to go up in pressure. All right, and then finally, I've got a few slides on the variety of X-ray microprobe applications. This one came from here, 13IDE. First author here is Tony Lanzarotti, beamline scientist. This is a study that shows in some quenched experimental glasses, it was a study of what happens to the speciation of, in this case, copper or sulfur, and these as the redox state is and the sulfur content is changed in the basaltic melt. This is what X-ray absorption spectra look like. This is one that's focused around the X-ray characteristic absorption edge of copper at 8.99 keV. And this one is at sulfur at a much lower 2.5 keV. And by doing spectroscopy around that X-ray absorption edge, you can see the details of the chemical speciation. And what he showed here is that if it's a sulfur-free system, then of course all the copper is in an oxide phase, but it only takes a couple hundred ppm, and then suddenly all the copper is in the sulfide. Then he's got information on the sulfur speciation as well. This shows the similar sort of technique for sulfur speciation, but this one's mapping. And here they've got a series of images at very finely separated energies, just a map at this energy, a map at that energy, map at that energy, map at that energy. And you can see how the absorption images change because of the variety of sulfur species that exist. This is a set of spectra from corals. So it's imaging of not only the sulfur distribution, but also the sulfur bonding type. in these corals, and they were able to coordinate that with a variety of minerals. And then I'll skip the last example because it's yet another microprobe example, and say, I hope you were not only encouraged by all the possibilities, at seas, but that you're going to be encouraged by the rock mechanics possibilities you see this week. And I want to remind you once more, please, once you learn here and you get excited about this, apply for beam time. SEAS has invested in these end stations because we want people to use them. And that means requesting beam time. Yeah, and enjoy the workshop. Any questions?
Thank you, Andy. Questions? Comments?
Yes.
You talked about this mixture of not zinc crystal, but not powder, but in between.
Yeah.
And so can you comment on the completeness of the data sets you collected? First question. And part B, the analysis of the data.
That's another workshop, Stu.
Yeah. Actually, it is another workshop, and I forgot to mention.
It's amazing.
So yeah, there is our next workshop, our next hands-on workshop is a hands-on workshop for data analysis of the multi-grain single crystal diffraction methods, and that will take place. That's the one that's August 8 and 9, sort of adjacent to our annual meeting. So
It's also here at APS.
and it's also no, it'll be on the University of Chicago campus.
Oh, okay.
Yeah, adjacent to the meeting. The completeness of the data is not as good as when you have ambient conditions and you can rotate the thing 100 degrees.
Yeah.
But we've designed diamond anvil cells specifically to maximize the rotation. So it's I guess complete enough, right? And there's sort of an assessment of the precision and and uniqueness of the refinement goes along with
If the
everything.
symmetry is very high, then you can get away with that.
Yeah, so that was a hexagonal thing.
Okay.
So
Okay.
that's right.
Okay.
But that's right. As you go higher and higher, you're going to need greater and greater openings and higher.
And then the analysis.
Then the analysis. It uses it bootstraps multiple software packages,
Yes.
right? So there's not one package that does everything, and there's different paths. I don't know what it is that you're asking about the analysis, but there's the, I guess it's Bruker, or I forget the alternative, but there's a couple different packages for just getting the data into reciprocal space. And then I believe that we've got machine learning methods are being developed to
Sort of the grains.
sort the grains.
Okay.
That's the hard part.
Yeah,
That's the
that's what I
part
mean.
that my PhD student would she spent weeks or months just gazing at the data, spinning it around in reciprocal space and looking for it to line up and saying, oh, there's a set of diffraction peaks that all belong to the same grain.
Okay, so it's an art.
Sorry, it's an art. Yes, that's right. That's right. So she managed to pull out a few dozen of what were probably hundreds of grain.
Yeah. Good. Thanks.